quick and give you kind of the now that you've seen the material already.
Mhm.
The progression is area to volume,
Right.
and like within area, there's between curves, the x-axis, and so on. Volume, you've got disk, washer, and then geometric shapes. Volume could lead you to surface area, among other things. And then kind of off to the side is arc length.
Mhm.
But like in terms of like what is most common, area, volume, and then maybe arc. I guess I'm saying surface area, unless you remember it being really emphasized heavily. Maybe not the right place to start.
Mhm.
But if you're okay with that, I'd like to start with 6. I think this
That's
is
fine.
more of a reasonable question to ask you as a final exam.
That's good with me.
Okay, set up integrals, one using disk washer method and one using cylindrical shells to find the volume of the solid obtained by rotating the region bounded by the curve, the y-axis, and the line y equals 1. So here's the line y equals 1 about the x-axis. That's very important there. So it's this region R. And I think the best way to start is the disk washer method. Okay. And a disk washer is integral from a to b, which in this case is 0 to 1, pi, and then it's your big R. Let me actually change this from, that could be confusing later on. We'll just call it this S. Big R squared minus little r squared dx. And in your case, big R is a constant. It's the 1, value of 1, because it's all the way to the axis there.
Mhm.
Your little r though changes. It's this curve right here, 1/2 x cubed squared dx.
Is the interval when you're rotating about the x-axis, do you use the y-axis as your intervals, like from 0 to 1?
It's the x-axis.
Well, the line, doesn't the line go from 0 to 2?
Oh, yes. Wait. No, it goes, I'm sorry.
Oh,
It
okay.
goes to, it's wherever, well, the truth is it's wherever this is, which I don't actually know where that is. I guess it's 1.2. But yeah, it's this value wherever like they intersect. They don't intersect at I mean, it's weird. If you put 1 in for y, it's 1/2 x cubed. It's the cube root of 2, which probably is about 1.2.
Okay.
But okay, but yeah. So the bounds come from the x-axis.
When you're rotating about the x-axis?
Yes, whatever axis you're rotating about, that's where the bounds come from.
Okay, all right.
Okay, now the next one is cylindrical shells. Okay, and it depends whether you're rotating around a horizontal or vertical axis. I actually need to look this one up because I don't use it very often. Cylindrical shells. Just loading the page here. Want to get the right formula for you. So the when we go about the x-axis, yeah. So the cylindrical shells is not ideal for this particular problem because when you go around the x-axis, which is what we want to do here, you need your volume as a function of x. So it's integral a of y dy, which it's not the preferred choice, I guess what I'm trying to say. But it's always, the thing is, whether it's a of x or it's a of y, it's always 2 pi radius times height, okay? But the radius in this case, that's usually your x or your y, depending on which one you're doing. And then your height is the other way. So because it's x axis, or because it's a horizontal axis, I guess the short of it is that this becomes integral 2 pi y, and then your height is top minus bottom. It's your no, I'm sorry, it's right minus left. So we have we actually need to solve this for x. So this becomes x equals the cube root, or 2y to the 1/3 power, and that's this curve here. And then I guess we do need that other one. So it's instead of y, we would use. See, I don't think you, okay, I don't think you would ever use cylindrical shells for this problem. Do you have the solutions handy? Sorry, I'm stumbling
Oh,
so
yes,
bad
I
on this.
do.
Maybe you could give me a little help here on this.
Do you want the answer?
Sure. Yeah, that might help here, speed this up, because I feel like I'm just stumbling on.
It says everything must be in terms of y. And the answer is the interval from 0 to 1, 2 pi y cube root of 2y dy.
Yeah. Okay. And that's what I was getting at by saying, you got to solve this for x. It becomes the cube root of 2y.
Why do you have to solve for x?
So because it's a horizontal axis that you're revolving around, it's in terms of y when it's a horizontal axis. See, there's this like it's like
isn't shells just backwards from disc and washer?
yes.
Okay.
Yeah, I mean there's almost like this like table, like if you're using disc, washer, and shell, if you're doing x axis, your horizontal axis, you're doing it in terms of x, but here you're doing it in terms of y.
Right.
And your y-axis is obviously in terms of y, but like you said, here it's in terms of x. So the preference is, if you have to integrate something over the y-axis, rather than using a disc washer, you use shell, because then you can turn it into an x integral.
Okay.
Which, like, we'd have to look at a problem that was designed that way so that you could see. Like, sometimes they're hard to do disc washer, whereas shell, they're much easier.
Okay.
All right, so I mean that didn't go great. To be honest, really didn't go well. Do you remember getting a surface area integral
Yes.
on a test? Okay.
Yeah.
Let me pull up the formula for that. I believe it's 2 pi ds. So the surface area integrals, I believe are, let me just confirm that here. More volume, work. Dark. You end up doing some of these again in calculus 3, but in more than one variable.
Nice.
But the two types here are, it's 2 pi y ds, 2 pi x ds, and again, it depends whether you're doing an x axis, excuse me, or a y axis. Your ds is dependent on that. So in the x axis, this one right here, it's square root 1 plus dy dx squared, and ds with the y axis is the square root of 1 plus dy dx squared. So again, like you've got X and Y, you got to know both of these. And now we can go do a problem. But they have to tell you, they can't, they can't leave this out. That's really important to know, what it is. So going to question 2. It says set up integrals to find the surface area by rotating the curve about the y-axis in 2 different ways. So I think I remember when we did this, like the y-axis one is I think the more straightforward one. The y-axis is 2 pi x ds. And actually, no, that's not the more straightforward one. The x-axis is the more straightforward because it's solved for y already.
Right.
So the x-axis one is integral 2 pi from 1 to 2 y, which is 2e to the x plus 1, and then square root of 1 plus the derivative of 2e to the x plus 1, but then you square it. To actually go about the y-axis, you have to do a few things here. The first thing is you need to solve for x in this. So you get y over 2 equals e to the x plus 1. And then x equals the natural log of y over 2 minus 1. Okay, but then you also need your bounds. When you put x equals 1 into this equation, you get 2e squared. And when you put x equals 2 in, you get 2e cubed. And those become your bounds on the y. So on the y, it's 2e squared, 2e cubed. That's why they say set up, but don't actually find it. 2 pi x now. So that's why we had to solve for x, natural log y over 2 minus 1. And then times square root of the derivative of this, 1 plus the derivative, which I'm not doing, but you can see what you can get it, and then you have to square it. Derivative and then square it. But the key here is which one, remembering that when it says 2 pi y, it doesn't really mean y, it means y as a function of x. It means right here it's x. This really means x as a function of y. This is solved for y. This one is solved for x.
Okay. And that's for rotating about
No, this is surface area. And
Oh,
they tell
right,
you, they have
yeah,
to tell you,
right.
they have to tell you though which axis.
Oh, okay. Okay, all right.
And without that, you can never do it. So just keep that in mind. Like that's a key metric for key piece of information where you can't even do anything until you have that.
Right.
So like we don't need to do it, but 8 is the same as that. Just have to it's already solved for one variable versus another. You just have to mix it up a little bit.
Okay.
All right, so I'll point this out. Question 1 and question 3 have nothing to do with calculus. Do you remember actually getting any of these volume formulas on the exam?
Like if they were given to us?
Well, no, like did they actually ask you to like find the volume of a sphere or a cone or a pyramid?
Ooh,
Like these seem really out of scope, but if you don't have the formula, you're stuck, or you got to figure it out.
right. I don't remember.
Maybe look, or if you don't have access to it, and maybe ask someone else in the class if you know anyone.
I don't even know where my third exam is, or wait, second exam.
All right. So let's move to 5. 5 is an arc length question. What is possible is that you might only be asked to set up an arc length question because there are very few that you can actually solve. It may just be a setup because it's really similar to the previous ones It's integral ds, where ds is the square root of 1 plus the derivative dy dx or dx dy, depending on which one it is, squared. So they have to give you a function. They have to give you the bounds. Okay. Once you have that information, the first thing I would do is take the derivative. I would say, what's y prime? Y prime is 2x minus 1 over 8 times 1 over x, and then square it. In this case, if you need a review on this, just spend a little time remembering how to expand binomials here. But
She didn't ask a like volume of that cone, by the way, on the exam.
okay.
I found it.
So like if you've got your old exams, like that would be another good thing for us to look through is like,
Right.
because that's the style, that's the like what she's emphasizing, and like they're going to pick questions that are kind of already there. There's two kind of thoughts that I've seen. One is like give students questions that they should know, like what do you want a student to know is getting out of calculus 2 to know. The other is to choose questions that nobody got right and hope that they get them right the second time. I don't really like that approach, but it's one I've seen. It's rare when they just like have totally different questions, like or like they'll take a question and they'll change it from x-axis to y-axis kind of thing. So there's like a few things you can do to really like kind of get an idea of what they're talking about there when they do this. All right, so this is what is this? This is multiply these together. What is that? 1/4, negative 1/4 x, or negative 1/4, then you double it, minus 1/2 plus 1 over 64 x squared. And then you got a 1. Huh. Okay, so this ds here is the square root of 1 plus all of this stuff. And my guess is this works out nicely. So you get 4x squared plus 1/2 plus 1 over 64 x squared. And I'm going to just guess that this is 2x plus 1 over 8x. And that does work. The reason it works is it's a perfect square trinomial. And what you're looking for is the square root of the first term, square root of the last term. When you multiply them together and then double it, does it give you the middle term? And it does.
Okay.
2x times 1 over 8x is 1/4. When you double it, you get 1/2, and it got the signs all right. This one really works out nice because when you take the square root of a square, you get just the thing left over. So you get 2x plus 1 over 8x integral from 1 to 2 dx. So that's x squared plus 1/8 natural log opposite value of x evaluated from 1 to 2. And we haven't done one of these ones, so might as well. So it's always top minus bottom. 2 squared plus 1 over 8 natural log of 2 minus 1 squared plus 1/8 natural log of 1. Natural log of 1 is 0. So you get 4 minus 1, 3 plus 1/8 natural log of 2. You find it. So if you want to send over any exam questions, I mean, you're welcome to. You can, if there's information that you're not comfortable sending, you always just cover it up. But
I do have my
that
first
is always
two exams.
Totally up to you. I'm gonna suggest we move to some work problems next. That's a big part of this exam. Or if you've got that exam and there's a work problem there you want us to look at, we can certainly do that.
Let me look at my first exam because I did worse on this one than did my second one. This one was like this is basically what we did yesterday. That's what we like reviewed for. Did that review over it.
Okay.
But
Are you gonna send that by text, drop it in the chat? What's,
Um, I want to work on this problem. It's a trig integral. I'm going to say it. It's not too complicated to say it. It's the integral of the square root of x squared minus 1.
like that?
Yep, over x to the 4th.
Any bounds?
Nope.
Okay. So this one, it has a type. And you got to know the type. Do you get a reference sheet
No.
for this?
Nope.
Okay. So it could be that she's gonna give it to you. It could be that you just need to memorize them. There's only 3, but I mean, with all the other things, you know, it's not like I know Pythagorean theorem, I mean, probably for the rest of my life, but this one I will not remember. You know, I gotta look this one up every
Yeah.
time. So this one, you've gotta get the right form. I actually grabbed the wrong form. Boy, that was dumb. This one is the secant form. Sorry. Oops. Like it does matter that x is first and not second. So here, like when I look at this, I say, oh, like 1 squared. So b is really 1. 1 squared, it means a is 1. And this is the one we want here. We want x equals a over b, which happens to be 1 over 1. So x is secant theta. And then you do 2 things. The first is you square it. Generally, that gives you secant squared theta. The next is you find a derivative. Derivative of secant is secant tangent d theta. Then you just sub in and you hopefully like see something good happen. It should, but you know, got to be careful here. Secant squared theta minus 1 square root over. So like what I could do here is like be like, well, x to the 4th is secant to the 4th theta. I'm not sure. I'm going to just hold off on that for just a moment here to decide that. But dx is secant theta tangent theta. So actually just a tiny bit more room here. So this is secant theta tangent theta d theta. And then now I do want to put that secant to the 4th in because I'm probably going to get a cancellation up here with it. We'll see. Is that okay so far?
Yep.
Okay. So this one up here at the top, you have to know your 3 Pythagorean identities. I've already forgotten this one. This one is there's a, so it's tangent squared theta plus 1 equals secant squared theta. If you move the secant squared over and I'm sorry, if you move the 1 over, you get secant squared theta minus 1 equals tangent squared theta, which means that this whole thing up here becomes the root of tangent squared theta. One of those secants cancels one of those, so you get secant to the 3rd theta tangent theta d theta, and then you see square root of tangent squared gives you just tangent times a tangent gives you tangent squared. So this whole thing becomes tangent squared theta over secant cubed theta d theta. I'm not saying this is any better, but it's closer. Any questions on that?
No.
Okay.
I just struggle with like trig integrals and trig substitution.
So there's, let me put this in the notes here before I go any further. We can keep going on this if you want, but there are the 3 forms that you're looking for, and they're right here. And then there's the 3, this in. There's the 3 Pythagorean identities that almost always accompany these.
Mm-hmm.
And they're like they go hand in hand. One goes with the other. You know, you're not, you know, if you're doing a secant squared one, you're gonna end up using the second one here. If you're using the sine one, you're gonna use the first
Right.
one, and so on. So then, you know, then to the question, well, how do you do this? This looks like a U substitution. Like U is either tangent of theta or U is either secant of theta. So what is the derivative of tangent? Secant squared theta. That kind of looks good. D theta. Not sure. Yeah, the derivative of secant is secant theta tangent theta. D theta. That one also kind of looks okay. So generally it's the bottom one. So I'm going to go with that first. So that would become tangent squared theta over U cubed. D theta is, sorry, that's du. Is du over secant theta tangent theta. Well, that gets rid of one of those. That cancels with that. Tangent over secant. So your sine over cosine, 1 over cosine. I wonder if we should have just done something there first. Yeah, I'm sort of like, well, what should we have done? So this could have been sine squared theta over cosine squared theta over 1 over cosine cubed theta. So that would get rid of those two, get rid of that. So this ends up being sine. Yes, there it is. It ends up being sine squared theta cosine theta. That's the right approach. So remember that problem we were doing yesterday where it said like make the U or make the U or turn it into sine and cosine? This stuff that I just did was no good because it didn't actually get us anywhere closer, whereas this one did, turning tangent into sine and cosine, secant into cosine. And then you get this. This one is a well-known one. U is sine theta, du is cosine theta, d theta. This ends up being u squared du, which gets really nice. 1/3 u cubed plus c. You put your u back in. Don't forget that. And then you're really supposed to do it back in terms of the original variable. And if like you've gotten this far, you might forget like, where did we even start? Like, I don't know, it's right here. and that's where you got to draw the triangle. So x is secant theta. Let me go do that down here. So x is secant theta. That means, okay, x over 1 is secant theta, but secant's really cosine. Cosine theta is the flip of this. So that's 1 over x. This becomes the square root of x squared minus 1. And then sine theta is really the square root of x squared minus 1 over x, opposite over hypotenuse. You know, tough problem. Lots of things here to remember.
So for like these trig integrals, are you wanting to try to find your way back to sine and cosine? Is that
Say that one more time. Just, I'm sorry, I didn't catch that. There was a cutout.
Like in these trig integral problems, are you wanting to like kind of navigate your way to have it where it's in sine and cosine?
Not always.
Okay.
Let me send you this. Let me see, integral Lamar integral reference sheet. There's a couple of, I'm trying to pull up here. There's a couple of different forms. Let me put this in the chat that you're looking for. And I thought we did this, but there's really these two forms that you're trying to get it down to. And one is sine times cosine. So to answer your question, like you said earlier, like, well, yeah, you kind of do, because if you can get into sine times cosine, there's always a solution. And then the other one is tangent times secant.
Right.
So like your goal, your game is to get it into one of these forms when you're starting out.
But we tried to get it to tangent and secant, but it just didn't work for that one, right? For the one we just did.
Yeah, because it was tangent over secant. it didn't
Yeah.
work. So that's why you try to go there. But there's other situations where you can convert it into sine and cosine, but you were onto something there. You really do kind of want it because these are like always doable.
But these, like, the rules underneath them kind of confused me.
Yeah, well,
when I was
there's too
taking the
many.
exam. Yeah.
There's too many. Which one? What did you get on the exam, or was this was the only trig one?
Let me check. I don't.
Was there like a cosine sine problem? You know, sine 7, cosine 6.
Trigging rule. I think that was the only one. Yeah, I think that was the only one.
So
Oh,
my
wait, no,
opinion
no,
would
no, no,
be
no.
okay.
Never mind. There was a integral of secant to the 4th times tangent x.
Tangent to the 1x.
Yeah.
Okay, so this is the second form, and
That's
it's
secant x. That's what it was. Secant 4 to the x, or secant to the 4x.
yeah. There's an x there. Yeah. So
Okay.
this is this is where m is even. Okay, so it's and I mean, like, how do you know this? I don't know. It's not
See, that's what confused, like the N and the M. I didn't realize like the M is like stuck, like only applies to secant.
right. So this is tangent 1x, secant 4x, n is 1, m is 4. And actually,
But N is odd as well.
right, so you actually could go either way on this. Maybe that's why our instructor gave it to you, to not, be weird, be difficult. I would go with the second one because you got secant squared x equals 1 plus tangent squared x. And if you square both of them, you get secant 4th x equals 1 plus tangent squared x squared. And that's what's going to go in there. Strip 2 secants out and convert remaining. Oh, I'm sorry. I guess so they want, actually, I'm sorry. They want you to do it differently. They want you to go tangent x, secant squared x. And then instead of this other secant squared x, they want you to write 1 plus tangent squared x like this. So this becomes, and then you distribute this, you get tangent x plus tangent cubed x. No, is that really what they say there? To remaining sequence to tangents, and then using substitution u equals tangent x. Oh, yeah, no, this is right. Wow. Okay. Oh, yeah. Okay. So the tangent x, secant squared x, 1 plus tangent squared x dx. And they say u must be, that's right here. It says u is tangent x. So why does that help? Well, u squared is tangent squared x. That's good right there. Du is tan x secant x. Is that helpful? Strip one tangent and one secant out. See, I'm saying like, well, this becomes 1 plus u squared. Great. The problem here, which I guess we can probably address, is that dx.
Would you move secant x over?
So you get this, and then there's a tangent x and a secant x. And the tangents obviously cancel, but there's 2 here. So you still have one secant there.
All right.
which is no good. Is this even right? Tangent, you said it's tangent to the 1,
Yes.
secant to the 4th?
Yep.
See, maybe. Tangent x, secant tangent cubed.
Would doing the other method, the other rule change anything?
The n is, if n is odd and m is even, n is odd, m is even, use 1 or 2. We can use either one. Strip 1 tangent and 1 secant out, convert remaining tangents to secants. But the problem is we have, we got to use this m is even. Strip 2 secants out, convert the remaining secants to tangent. I'm missing something here. U is tangent x. Du is tangent. No, du is secant squared x. That's the issue. I'm sorry. That's the problem. Now it works.
Okay.
That's why it's supposed to work. Secant squared x dx. So what that does is it gets this to be secant squared x here. And then instead of this tangent, you get a u, secant squared x. Those cancel. And you get integral u times 1 plus u squared du. Distribute in u plus u cubed. And then you got it.
Okay.
The nice thing is with the notes, you'll be able to see like how to cut through all that.
All right.
And get there. Obviously it didn't happen live.
Let's see. Is that?
This wasn't a this was not a trig substitution. This was a trig
Just a trig integral.
functions with powers. The trig integrals are the ones where you have the like this form where you have to have a square root generally.
That's trig substitution.
Those are considered trig substitutions, the ones in this blue picture.
All right. Okay.
The ones that
Yeah.
the ones that we just did, they're considered product and some quotients of trig functions.
I struggle with those. And can we do? I have another problem on the first exam. It's interval from 0 to pi of x squared times cosine of x cubed.
Is it cubed here like this?
Yep.
All right, so you're not, this one is just a u sub because the derivative of du is right there. It's right there. So if you're going to go to the trouble of u sub with a definite integral, often it's better to evaluate the integral at both end, I'm sorry, the function at both endpoints to get new bounds. So you put 0 into your u, pi into your u, so it goes from 0 to pi cubed. X squared cosine u, because u is your x cubed, your dx is du over 3x squared, like that. And then you can see that they cancel. So this becomes 1/3 integral 0 to pi cubed cosine u du. Antiderivative cosine is sine u, and you got a 1/3 there. Now, since you changed the bounds, you just evaluate it at the new bounds. You don't have to back substitute. This one doesn't work out great. It's sine pi cubed, which is not a known value, it's just whatever it is, minus 1/3 sine 0, that is 0. Sine is 0, 0. So it's just this. U subs are kind of the kind of the ones that you hope you get a lot of because they are the least amount of work.
Right.
If you tried integration by parts, okay.
Yeah, I was thinking I didn't even recognize those U sub.
Yeah.
And I see 2 functions. I'm already just like integration by parts. which probably
Yeah.
is not a good thing.
You gotta be careful because it's yeah, just there's like if I had the integral of the cosine of natural log of x over x, this is like your classic problem. Your u is natural log of x because du is 1 over x dx, which is already in there. And that's why it's so important that you try u sub first. Like it's like try factoring.
If I see a
Don't go
function
to
inside of another function,
often it's u sub. Yeah.
just try it. Just go ahead and try it. If it doesn't work, then
That's actually a good observation. A function inside of function is almost always u sub. Yeah. Because if I gave you like e to the x squared minus 3, this is the more common problem. I'm not going to give you, yeah, because I keep your integration by parts is, you know, variant of some sort of polynomial, but it's e to the x. It's not e to the x squared. So that's a good observation. If it's a nested function like this, a composition is the right mathy word.
right.
Like you have here, yeah, it's generally u sub.
But then, like that trig integral we just did, x squared minus 1 is a function inside of a function, and we had ended up doing trig integral. U sub.
Oh. Yeah, that's true. That's true.
But I
There's
guess
always
that's just
exception.
recognizing that that's a trig integral because of what it is.
Yeah. I mentioned this at one point when you're taking a test, like sometimes just identifying the type is a good way to study,
Right.
not necessarily going through all the, because you're never going to exactly pick what integral you're going to get. Just maybe finding a practice exam and from somewhere else on the web and just like calculus 2 practice exam and look for, you know, integrals and see if you can figure out what method they used before they went and solved it.
All right. Alrighty. Let me see if I can find another problem. That one won't, that one is not a short problem. Trying to find just like a short, quick problem we can do. Okay, there's a question. It's not like we won't have to work it out, but I'm gonna read it. It says, set up an integral for the volume of the solid located between x equals 0 and x equals 5, whose cross section at each x is a square with side length x e to the x.
Like this.
Yep.
Okay. This one isn't bad.
And I put the volume equals integral from 0 to 5 x ex cubed dx.
So this is the side length, right? If the cross section, it's a square.
Volume.
Yeah, we're gonna get to volume. So volume is always it's just the area function dx, and you added an extra power because this one's x e to the x and this is x e to the x.
Right,
So
but I thought it was cubed because I'm setting up for the volume. I thought it was like the volume of a.
The volume is the whole thing. So the dx is the third dimension.
Okay.
Because you're doing these slices, and they're a thickness of dx. It's like if you hold up a piece of paper, and you imagine that being your cross section, it's a thickness dx. So when you add up all the dx's, which is what the integral is, that is your volume.
Okay.
You got
So
that
it is
one, you get the one right next to it, and so on.
Okay.
If
Yeah, I
you've
was
ever pulled
confused.
out
I got that
a
wrong. Yeah. Okay.
well, you just your power is wrong.
Right. Yeah.
Like
Yeah.
like to me, that's almost a minor thing. Somewhere it wasn't conveyed to you that the volume occurs because of the dx, not because of the area function.
Okay. She took half the points from it. Just
Well, that's too many. Go talk to her and tell her that's too much.
Well, I won't see her again after Wednesday, so.
It is a good idea to talk to your professors in college, even as
Uh-huh.
awkward as it may be. They often want to know that there's a real person there taking the class, and sometimes they take that into account when they're grading you.
Okay.
You know, if you came to office hours, if you ever emailed them, or
Right.
you'd be surprised how just even the minimal effort goes a long way.
Mhm.
You know, when things like this that are very subjective when grading wise.
Right. All right. Well, that's all I got right now.
Okay, so you for sure want to do something tomorrow morning, like 11
Yes.
a.m. your time. Okay. When will you be at a computer to book it? Because I don't want to put it up
Right
and
now.
then somehow have somebody else grab it. All right, let me do it right now while we're on the call, and then I'll let you know that it's there tomorrow, Wednesday. There it is. Oh no, tomorrow's Tuesday. I'm way off.
Yeah, I thought today was Tuesday as well.
Yeah. There it is. All right, should be there. Thank you, Trenton. I'll send you the notes here shortly, and I'll see you tomorrow.
All right.
Have a great night. Bye now.